Hi dear students, welcome to today's online class. Today we discuss one example for two component system involving formation of compound with incongruent melting point. In the previous class we have discussed the general phase diagram of incongruent melting system. Here we have an example. The system is sodium sulphate water system. Obviously, it is a salt water system, so that the compound formed will be salt hydrate. See that this is a 6-phase system where the phases are ice, the solid forms are ice. Sodium sulphate has two allotropic forms, that is rhombic and monoclinic. Then there are two hydrates formed here, that is Na2SO4 10H2O and Na2SO4 7H2O. And also there will be solution. So altogether there are 6 phases. So here we are plotting temperature composition diagram. Let us explain various parts of this phase diagram, starting with point A. Point A is the melting point of ice, 0 degrees Celsius. And let us consider various curves. First of all, curve AB. This is curve AB, which can be called melting point curve of ice or freezing point curve of water, which indicate how the melting point of water decreases on adding increasing amount of sodium sulphate. The next we consider the curve BC, this one. This is the curve of solubility curve of Na2SO4 10H2O decahydrate. We can call it solubility curve of sodium sulphate decahydrate. So the two phases in equilibrium will be Na2SO4 10H2O solid in equilibrium with the solution. Then the third curve is CD, this one. This is the solubility curve of rhombic sulfur, one allotropic form of not sulfur, sodium sulphate, where the two phases in equilibrium will be rhombic sodium sulphate crystal in equilibrium with the solution. And finally we have the curve DE. This is the solubility curve of the second allotrop, that is monoclinic sodium sulphate crystals in equilibrium with the solution. So these are 4 solid curves along which there will be two phases in equilibrium, so that the system will be monovariant. F equal C minus P plus 1, that is 2 minus 2 plus 1, so 1. Monovariant, two phases in equilibrium. Now what about the area enclosed or above the curves? That means this area. It's clear it represents a single phase, that is the unsaturated solution or the liquid phase only, so that the system will be bivariant there, because C minus 2 minus 1 plus 1, so F equal 2. All the area coming below the curve, like here, all these areas you can see, it is only, these are all representing two phases in equilibrium, so that it will be all monovariant. So this is bivariant, all these areas are monovariant, F equal 1. And now let's see what are the invariant points or triple points here. Before that, you can see there are some broken lines also in this phase diagram. One is, we can call them as metastable equilibria, as you know. When there is supercooling, when there is careful cooling of the system, we get such metastable equilibria. One is this broken line BG. That means it is the extension of the curve AB. AB is the melting point curve of ice, where ice in equilibrium with the solution. If you cool such a solution very slowly, actually at B, another compound has to be formed, that is 10H2O. But if you cool it slowly, you get an extension that is BG. So we can call it metastable equilibria or metastable melting point curve of ice. So what are the phases in equilibrium along BG? It will be ice and solution itself. Actually at B, 10H2O has to be formed, but it doesn't happen. Then next metastable curve is this one, that is GF, this curve GF. There we can see a new compound, a new hydrate formed, that is 7H2O. It's a metastable hydrate formed. So GF is the solubility curve of sodium sulfate 7H2O. It's a metastable solubility curve of sodium sulfate 7H2O. And finally, next we have CF, this curve. That is the extension of the curve CD. That means if you carefully cool, this DC will extend to F. So CF is the metastable solubility curve of rhombic sodium sulfate. So the phases in equilibrium will be rhombic sodium sulfate and solution. There is one more metastable curve, that is CH. What about this curve? It is the extension of BC. What along BC? Along BC, sodium sulfate 10H2O in equilibrium with solution, or that is the solubility curve of 10H2O. So the dotted curve, the broken curve CH, can be called the metastable solubility curve of 10H2O. Right? So these are various solubility curves, various metastable curves. Along all these curves, F equal 1 system is monovariant because two phases are in equilibrium. Right. If you look at this, this diagram, you see, this diagram is more simple and you can clearly notice what are the phases which appear along various curves. It's clearly shown there. Like here, it is the ice which appear along this curve. Along this curve, the yellow curve, that's a solid curve. Next curve here, 10H2O appears. Here it is rhombic sodium sulfate. Here is monoclinic sodium sulfate. And this broken, the dotted line down, here it is 7H2O appearing. There is a correction in this diagram, that is this the curve shown here, that is FD, that is shown bold, but it's to be broken line because it's a metastable equilibria. That is, this curve is to be broken line. Okay. Fine. Now going back to the previous diagram, what is left is to explain various invariant points, right? Okay. First of all, point B, you can see very clearly see that it is a eutectic point. So 3 phases in equilibrium, 2 solid and 1 liquid. Which are they? That will be ice, Na2SO4, 10H2O and solution. Eutectic point, 3 phases in equilibrium, invariant. Then next is point C. This point C is very important because it is a peritectic point where Na2SO4 10H2O incongruently melt into Na2SO4 7H2O and solution. So that's a peritectic point. So peritectic reaction here is Na2SO4 10H2O melts into a liquid having different composition and another solid, that is 7H2O plus solution or liquid. This is the peritectic reaction taking place. So that is also invariant because 3 phases are in equilibrium, right? So it is a peritectic point and it is invariant. The next is point D. What is point D? Point D shows what is called a transition point. Why? Because there occur a change of rhombic sodium sulfate into monoclinic, allotropic transformation only, right? So it is called transition point. There are also 3 phases in equilibrium, rhombic sodium sulfate, monoclinic sodium sulfate and solution. That is again invariant. Now we have 2 more points which are also invariant, which are actually metastable points. Which are they? First of all, point G down. You know this curve BG is a metastable curve. Naturally, point G will be also a metastable triple point. It is actually metastable eutectic point. What are the phases in equilibrium there? It's clear. You can just look at the curves and predict. The curve AG, AB or AG represent formation of ice, so ice. Then curve GF represents 7H2O, so solid heptahydrate, and solution will be in equilibrium. That's also invariant. Finally, the point F here. This point F is a metastable point, metastable transition point. See, point C we discussed, that is the peritectic point. Likewise, point F is also a peritectic point, but it is metastable. At point C, phases in equilibrium are 10H2O, rhombic sulfur and solution. Whereas what about at F? F it will be Na2SO4 7H2O, rhombic sodium sulfate and solution will be in equilibrium. That is also a peritectic point but metastable, and it is also invariant. So what is the peritectic reaction taking place at F? It will be Na2SO4 7H2O. It will melt incongruently so that the liquid will have a different composition compared to the solid. So Na2SO4 7H2O decompose into sodium sulfate rhombic form plus the solution or liquid. So it is also invariant and it is also a peritectic point. So these are various aspects of the phase diagram of sodium sulfate water system. Thank you.